Good morning. Our last class was about horizontal alignment, which is the first part of our design project. I also made some calculations, which you can see in my previous video. And today classes, my video will be about the second part of our design project, the vertical alignment. As I told you in the last lessons, we have three groups of elements on which our railway lines are designed. The first of them was the horizontal alignment. Today we will talk about the second one, the vertical alignment, and in the next lessons we will discuss the third one, the cross section. Elements on the vertical plane, vertical alignment, consist of two key sections: the section with the constant gradient and the sections of curves. These sections of curves can be either made as a parabola or as sections of the circular curve. In order to understand the design in the vertical alignment, we need to explain what the gradient P is. According to the definition, the track gradient is the measurement of the slope or incline of a railway track, typically expressed as a percentage of ratio indicating the vertical change in the elevation over a given horizontal distance. The track gradient is usually given in perimeters. An example, 1,000th of a millimeter. It is also said that the slope of the track gradient is millimeters by meters. The track gradient's value of track P should be limited due to the moving trains and available brakes of these trains. Normally, there are no upper limits for the length of sections with constant track gradient, and only the lower conditions are set. You can see the lower conditions in table 21. The normal limit, the minimum length of the section, is 20 meters. However, in exceptional cases, it may turn out that there is no lower limit. In example, as you may see, the limit is 0 meter. What is also important is that the standard does not specify any upper limit values. These values are proposed in the technical specifications of the interoperability in the ENF part. In a moment, I will show you these values look like. But before we go there, I would like to emphasize that there are certain situations in which the lower limit can be increased. For example, if we have the appropriate rolling stock, as you have marked on this slide. Yes. The technical specifications of interoperability, ENF part, in point 4233, provide three cases for the maximum gradient. The first of them says that for new railway lines at platforms, the inclination, the gradient, should not be greater than 2.5 millimeters per meter. The second condition says that for new stabling tracks intended for parking rolling stock, should not be more than 2.5 millimeters per meter. And the third most interesting case, that is for railways lines, for new categories P1, dedicated to the passenger traffic, the maximum gradient value should not be greater than 35 millimeters by meter. And with this assumption, we have also two additional conditions. First one, that the gradient along the entire length of 10 kilometers will not be greater than or equal to 25 millimeter per meter. And second one, that the maximum length of a constant maximum gradient of 35 millimeters per meter will not be longer than 6 kilometers. And these assumptions you can adopt in your projects. The standard EN 13803 defines punctuation on vertical curves. For these curves, you should choose the appropriate radius of the vertical arc. You can see the vertical arc and the radius of the vertical foot. You can see the vertical arc and the value of the vertical arc radii in the table number 22. The choice of the radius depends on the conditions you see here, as well as what kind of arc we have. As a rule, in our design projects, we will have circular arcs. It is also worth noting that some arches are convex and concave. You can see both of them on the slide, and you can see also the difference between them. In addition to the typical minimum values of our vertical curve radius, the standard defines a certain parameter RV for which we have calculated the minimum value of the vertical arc depending on the maximum speed. The RV value is determined by the 12th formula and by using the numbers from the table 23. As you can see, here we have kind of calculation that we can somehow present on a specific example. Assuming that our speed v is 160 km per hour and that we have a convex arc, we can assume that our RV is nothing more than 0.35 times 160 squared. Then we get the value of 8,960 meters, and we can round it to a certain module value, which I propose here. And then the value of RV mean is 10,000 meters, and we can treat this value for our conditions as the value of the radius of the minimum vertical curve. 10,000 meters. If we have a defined curve radius, we need to ask when we must to apply the curves. Point 6.17 tell us about the average change in the gradient, the delta P, for which it is necessary to consider the introduction of the vertical arches. And in the table 25, the parameters are specified. Limit value, the upper limit for changing the track gradient delta P, is defined for two conditions. To the speed of 230 kilometers per hour and from the range of 230 to 360 kilometers per hour. As the upper limit is 1 millimeter per meter, while for others, as you can see in the table, other values are specified. So our calculations lead to the fact that we simply have to determine when the difference between the two nearly track gradients is greater than 1 millimeter per meter. It is important to remember that we have concave and convex arches, and depending on that, we have certain sign rules. If we have a downhill gradient connected to an uphill gradient, then we use formula key point 6. We sum the p-values. In other case, we subtract two parameters. And also, we must remember that the upper limit is 1 millimeter per meter. And this is the whole design of vertical alignment. It leads to the design of track gradient and possibly of designing the vertical circular curves. So now we can move on to the practice based on which you will perform a vertical alignment for your railway line. We recently finished a project on designing a horizontal alignment for our railway line. It included straight lines and circular curves. Now, all we have to do is to make the railway line profile, the vertical alignment, based on the designed horizontal alignment. First, for the entire length on our road, we perform a leveling survey. It consists in the fact that for each layer of the terrain, the ground contour, we measure the length of our railway line. Then we mark these values along the entire length of our railway line, creating the terrain elevation profile. Only after completing this activity, we can go directly to design of our railway line, our vertical alignment. For our defined ground profile, we will introduce sections with a constant gradient P. Remember that the maximum and minimum values are also to remember the maximum and minimum value, and also that if it's unnecessary, we design vertical curves. The rule is that we try to adjust to the ground profile as much as possible, as you may see on this slide. Yes, here are the gradients, here are the constant gradients sections with constant gradient P value. Also, we introduced certain markings, the length of the sections with a constant gradient P, the value of the vertical arches, and the additional values of the horizontal alignment of our railway line. Our next step for our next classes will be the design of the cross sections. And for today, that's all. If you have any questions or want to consultations or advice, I'm here for you. Thank you very much. See you soon. Goodbye.